welcome to video notes 9. I'm going to try some new notation there for you so you can maybe organize your notes if you're in my class. But this is polynomial components part 1, and we have quite a bit to look at here. So first off, a polynomial can be built in standard form or factored form. And if we look at the standard form, this is the type of polynomial we're used to looking at. So if you want to put an example there, it could be something like 3x to the fourth plus 5x squared minus 2. So we've got decreasing degrees when we start with the leading term being 3x to the fourth. So that's going to be the form you most likely will see these polynomials in. You could also see a polynomial in its factored form with the x-intercepts given as these c values. And notice there's an n number of factors because we have n degrees in this polynomial. So this is the same polynomial written generically twice, just in two different forms. And something we need to maybe remember or pay attention to about the degree of the polynomial is there are n amount of x-intercepts, and some of them could be non-real. So we'll look at some specific cases when that pops up, but not right now. And there are an n-1 amount of terms in our polynomial. So if you take the polynomial x cubed, that does not have a maximum or minimum in it, actually. It has two terms, however. So this cubic shape is going to be kind of a special case, but it still represents those two terms that all polynomials have. And this cubic shape could reappear in another polynomial depending on the factors. So we could have a cubic shape that, if I can zoom in some, that goes through a 0 like so, and then the rest of it kind of looks like a quadratic. Anyway, we'll get into combining those factored pieces in another video. But right now we're going to focus on n behavior. So we've actually seen n behavior with quadratics. And I've got a few examples here which you might want to pause and write down. The first one is kind of standard form of a quadratic. And in the standard form of a quadratic, we can tell what our a value is, and we know the degree of our quadratic. So if our quadratic is negative 6x squared, plus 1, that negative 6x squared is telling us that our polynomial, our quadratic polynomial, is facing down, and both ends are facing down. So we can represent that with a little thumbnail, sure, but most of the time we won't see a thumbnail as an answer we can put. We'll see this notation that says, as x approaches infinity, what does y approach? As x approaches negative infinity, what does y approach? Based on the little thumbnail I have, and based on what I know a quadratic does, especially this quadratic, I know that these y values are pointed down, so they're going towards negative infinity, and both of them are going towards negative infinity. In another example, we see vertex form here. If we were to multiply this out, we would get a leading term of 4x squared. So this means our quadratic is facing up, so our y values are going up to infinity. And in this form, the factored form of a quadratic, we see the leading term, I'm just multiplying here, negative 2 times x is negative 2x squared. And no matter what is going on with the numbers in the other factors, it will not dictate the end behavior of our quadratic. We know this is a facing down parabola. So a lot of these concepts, all of them, are going to hold true for these polynomials that we're about to look at. It's just that we have more degrees to reference. So we have a little bit more of a layer to peel back. So real quick, let's look at kind of what the quadratics were doing. If you have an even degree polynomial, like a quadratic or a quartic, or any even degree, then you are always going to have these two scenarios. If the leading coefficient is negative, then we'll get this shape over here in this box where a is negative. Remember, a is this number that's in the it's on the leading term of the polynomial, no matter where you look. And a is positive if the ends are pointed up. And then the case that we don't have with quadratics, but we have with some polynomials, is an odd degree. So we know odd degrees could look like this: x to the fifth. X to the 1 is not, that would be the leading degree, and that's not a polynomial, that's a linear function, so we don't look at that. Right, so we can look at these as examples. So if the leading degree is positive, then the right side of the polynomial will be pointed up. So as x approaches infinity, y will approach infinity. And I like to remember the cubic function, and also, if you can't tell, I like to draw little thumbnails for myself. It saves on memory space. And that way I can remember what's going on with that limit notation. But this would be an example of a positive a value on an odd degree polynomial. And then the negative a value on an odd degree polynomial would point down in the fourth quadrant, or towards the fourth quadrant on the right side of the polynomial, and then it would point up on the left side of the polynomial. And to help you remember, you can make a little thumbnail, you can make a little square like this. So an odd degree polynomial that is positive would be up to the right and down to the left. An odd degree polynomial that has a negative a would be up to the left and down to the right. Even's pretty simple, both up or both down. I'm putting in a few extra squiggles there. Yeah, so those would be examples of the end behavior on those type of polynomials. And I wanted to look at some examples. These three examples, A, B, and C, actually have factored forms, which I went ahead and factored. If you would like to pause the video and challenge yourself with how to factor these, I recommend doing that. But I am going to show how to do it. Okay. So if we're factoring negative x cubed plus 4x, then we're factoring out the negative x, and we have x squared minus 4 left over. And then this is a difference of squares, so that's why we get these two factors. In B, we have what looks like a quadratic form. So remember we used u substitution. Well, you can use it here to factor, and I know that my factors end up being x squared minus 4 and x squared minus 1. And then to continue factoring, we have to use a difference of squares to get this set of factors and the other set of factors that corresponds to x squared minus 1. And then lastly, this polynomial has a factorization that has a greatest common factor of x, and then what is left over after we factor out x is a difference of squares. But not only is it a difference of squares, it also has, well, it's a difference of squares once, and then it's a difference of squares again. So we've got x squared plus 1 and x squared minus 1 that come out of x to the fourth minus 1. And then this factor produces another difference of squares. So we completely factored this polynomial. And we didn't have to do anything special with these factorizations. We just had to remember greatest common factors and difference of squares, really. This middle one had u substitution, but it wasn't that challenging of a one. Now, I did that pretty quick. Obviously, you would have a little bit more time to do that if you were asked to do so. Anyway, why did I do that? We'll end up looking at the left and right hand behavior of these factored forms as well as their standard forms. So looking at their standard forms, I've got the negative a, so a is negative and it's odd. So as x approaches infinity, y approaches negative infinity. So remember, this would look like a polynomial like that. So y has to approach positive infinity. For b, as x approaches infinity, y will approach infinity, and y will approach infinity as x approaches negative infinity. So this polynomial has its ends both face up because a is positive and it's an even degree. This is an a that's positive. Over here on c, it's 1, positive 1, and the degree is odd, so the right end points up towards infinity and the left end will point down towards negative infinity. And we should be able to tell that from our factored forms as well. If we pay attention to what contributes to the leading term, so the leading term, if say we didn't have these lovely standard form equations and we only had the factored forms, if we pay attention to the variables in each factor which contribute to the leading degree, then we see negative x cubed, and we'll end up finding the same result that we did in the standard form case. So as long as we're able to pick out the variables that contribute to the leading degree, then we know the end behavior as well. So this is x to the fourth. And over here, we have a little bit more to multiply together. Oops. But nonetheless, we can find it. Yeah, so that's 5x's. And there's no negative coefficient there, so it's a positive x to the fifth. Alright, cool. So we would get the same, if you were asked to start with the factored form and determine the end behavior, then you could do that as well. Okay, here we are on the second page of extrema, maxima, and minima. We are determining the interval, so we're using interval notation again, where a local maxima or local minima occurs. And we're going to do that based on the x-intercepts we discover. So these x-intercepts are going to serve as little anchor points to kind of narrow down our search for the maxima and minima. Sort of like a neighborhood. The terms we need to know are listed here, so local max, local min, and absolute max and absolute min. They're pretty self-explanatory, but we are asked to determine the interval bound by x-intercepts that contains the local max and min for a, b, and c. And if we can, then we're going to state the exact x value of the max and min. On a, this is the same function we looked at before on this a next to the end behavior section. The maximum y value, the local maximum y value, can be found on the interval 0 to 2. So on this interval, the maximum occurs right in between there. The minimum will occur on the interval -2 to 0. So we're just making sure we list these things appropriately and are reading the graph easily enough. On B, we have two minimums, and they occur on two different intervals. So we'll have the interval -2 to -1 and 1 to 2. And then our maximum is going to occur between -1 and 1. And then we know that max value has an x value that equals 0, because we can see right here where that maximum is. If it's not readily apparent that the graph is showing where the maximum is, then it's best just to leave it as the interval. On this last graph of C, we have a minimum on the interval 0 to 1, and we have a maximum on the interval -1 to 0. So I'm just checking the y values of my graph. So we will have some graphs with these equations. And this is just another way to describe what's happening on the graphs. Now letter D is giving you the x-intercepts. So they're listed here. So 0, 0 is right here. It's the green one. 1.50 is about right there. It's a little bit past 1.5. And 5.1 is right here. So we are determining the intervals that contain the local max and min. So same deal. The max, I should say min, the minimum occurs between 1.5 and 5.1. So that's a local max, or sorry, local min. So we can say at x equals 4. It's pretty apparent that's the lowest y value if we follow 4 all the way down. But I also see another one. At x equals 0, we have another local minimum. So this is a bit strange because the graph never goes negative. So we don't have the graph coming down past the x-axis. So this graph doesn't go down and then come back up to go to that value. Instead, it sort of bounces off the graph there, off the x-axis I should say, and it still produces a local minimum. So don't mistake that shape when you see it in the future. And then we have a local max between 0 and 1.5. And we can't tell what it is, so we're not going to say. It does look like it's at 1. Oh, I guess we can tell what it is. Yeah. At x equals 1. Yay! So it's right there. And this is for advanced only, so we're given the extrema of the polynomial. So we have the maximum occurring at x equals 1, and we have the minimas occurring at 0 and 4. On what intervals is the graph increasing and decreasing? So for increasing intervals, this graph is increasing from, I'll do it in blue, from 0 to the maximum, and then from minimums to positive infinity. So we have to pay attention to end behavior on this graph. So it's increasing from 0 to 1. And we use parentheses. It's also increasing from 4 to infinity. This graph is decreasing, which I'll put in yellow, from the x value is negative infinity, and then we start at the maximum and work our way to the minimum. So this is just as hard as making sure you're moving left to right and you're working your way down and right or down and up, which down and right would be decreasing here. So we've got negative infinity to 0, not included, and then 1 to 4, not included. Okay, so that wraps it up for this lesson. Make sure you check out your practice for your class, and I'll talk to you later. Bye.